Hi, welcome back. My name's Owen Lockwood, and today I'll be talking about the 2021 Physical Review A paper evaluating the noise resilience of variational quantum algorithms. In this paper, they provide a number of numerical experiments to look at the performance of variational quantum algorithms under different models of noise. So the first thing we're going to want to do is look at exactly what the problem setting is. So in this problem setting, we have our density matrix here denoted by a rho of a parametrized function denoted by the parameters theta that is some combination of unitary operations. So we have multiple layers of these unitaries, UL to U0, applied on the ground state or initial density matrix denoted here by rho 0. So in this formalism, we now can look at what the measurement operator is. And in this case, we're going to be considering an arbitrary operator, O, applied on this density matrix. So in this case, we're looking, this notation here is a trace of this operator applied on the density matrix is basically the expectation value of this operator. And this operator in this work is largely going to be Hamiltonians, or considering different problems for the variational quantum eigensolver, but there are going to be some other considerations. And this formalism is general to whatever your measurement and operators may be, and you could even pass this into another function that's differentiable or even non-differentiable and propagate that error through. So now let's take a little bit of a look inside this density matrix here, rho. This density matrix is a way of representing our quantum system in the presence of noise. We formalize it here as the sum over where this is P and this is rho. You'll notice this little swirl here where P is the probability of this, of the outer product of our quantum states, of our possible quantum states. So you'll notice that in the case of a non-mixed state or a noiseless pure state, we have our probability equal to 1 for this setup. We have no other possible states. So this will just be the outer product of our quantum system. In the presence of noise, however, we do not have the exact knowledge of what our system is. So we represent it as whatever our probabilities are plus our possible systems. So that's a way that we use this density matrix to represent our quantum system in these noisy scenarios. So when we want to evaluate this system, we have a number of metrics we can use. The first of these is simply the energy, or the cost function. So simply, what is this number? And so we're trying to minimize this function, obviously, so the lower the better. And so this metric we're going to refer to as the energy in the case that it's Hamiltonian that we're considering with. And this is probably the most common metric that you'll see. A lot of papers you'll see the varying energy under different distances of bonds or something like that. So that's a common metric. Now we're going to also consider some less common metrics in the case of variational optimization. The second of these is the fidelity. So the fidelity, here denoted as a function f, basically tells us the similarity between two quantum systems, sigma and rho. Here we're going to assume that sigma and rho are both density matrices. So this is equal to the square of the trace of the matrix square root of the matrix square root of rho times sigma times the matrix square root of rho. So this is 1 when these systems are identical. If sigma and rho are the exact same system, then this will result in 1. If they are not the same, this will result in a number less than 1, bounded by 0. So this metric gives us an output between 0 and 1 that basically tells us how related these states are. In fact, you can actually reduce this more, and you may be familiar with a lot more reduced cases where if these are pure states or non-density matrices, they can just be state vectors, you can reduce this equation to be much simpler. But because we're going to be dealing with a noisy scenario, I'm going to be leaving it in this format. The third metric that we're going to be looking at is called the concurrence. So the concurrence here is denoted by the letter Q. And this is on our density matrix. Here I'm denoting it with a prime for a reason you'll see shortly. And this is basically the max, so it's bounded by 0, lower bounded by 0, of the difference in eigenvalues. So we have lambda 1 through lambda 4, where these are the sorted eigenvalues. This is the largest eigenvalue and this is the smallest. And so this difference will give us information on the entanglement of this state, where if the concurrence is 1, we have a maximally entangled Bell state, and if the concurrence is 0, we have no entanglement. And so you'll notice with 4 eigenvalues, this is a descriptor for a 4x4 density matrix. So this is only really applicable in this formalism for 2-qubit systems. There are techniques that you can modify this with to get it to apply to larger systems, but we're just going to focus on this 2-qubit example. So now let's look at why I denoted this density matrix with a prime symbol. And that's because it isn't just the density matrix that we were looking at earlier, it's actually the density matrix plus some spin considerations. So specifically, we have this prime is equal to the Kronecker product of our poly Y matrices, where sigma sub y denotes poly y, and this big O times denotes our Kronecker product of these Y matrices. And then we have our density matrix that's from over there, denoted with our dagger because it's the conjugate transpose, and then we once again multiply it by the Kronecker product of our poly Y spin matrices. So this is what actually gets plugged into the concurrence equation. So now that we have some metrics to measure the energy, the fidelity, and the concurrence, which tell us information about how our routine is performing, what the entanglement looks like, and how our desired state comparison is, we can now look into the noise modeling aspect of this. Specifically, we're going to assume that the noise has some constant effect for every layer. Specifically, we formalize this where we now have our noisy density matrix here, where that was actually in the absence of noise, where we have our noise operation denoted by this symbol at a given layer, followed by our unitary at that layer, continuing on till our initial application on our density matrix. So this is an assumption about what the noise looks like. We're assuming that it has a constant acting on every qubit, and we're assuming that it's consistent after every one of these unitary layers. And so this is obviously an assumption. Not all noise on hardware looks like this, but it is a useful tool to evaluate these noise results. So now let's take a look inside what's going on in these noisy systems. So this noise operator is mapped to our density matrix using something called Krauss operators. So these can be non-unitary operators that just have to be trace preserving, that you can operate on our density matrix to get the new noisy density matrix. So for however many Krauss operators represent this noisy channel, we have K sub I, where this is one of our Krauss operators. Then we have our density matrix here, and then we have the conjugate transpose of this Krauss operator. And so this represents our noisy channel. And so in this case, this noise channel can be, there's many different kinds, but we're going to be looking at 3: phase dampening, amplitude dampening, and depolarizing. So let's jump into those and see exactly what those Krauss operators are in those cases. So the first one we're going to be looking at is this phase dampening. So the phase dampening is the 2 Krauss operator noise represented by K1 here, which is the 2x2 matrix, 1, 0, 0, square root of 1 minus gamma, where all of these are going to have a gamma parameter that's basically a tune on how much noise there is. You can see in the case where gamma is 0, this simply reduces to the identity matrix, so there's no operation being done here. And in the case of K2, we have 0, 0, 0, and square root of gamma. We can see that in the case of gamma equals 0, this is an all 0 matrix, so we'll simply eliminate that sum component for our noise channel. So this is phase dampening. Next we'll look at amplitude dampening, and this basically is what pushes the amplitude of the one state, or the excited state, down. And this is common in real hardware because when we're exciting our state, whatever we represent our physical qubits as, when we excite them, they're not at their lowest energy state, and they want to go back down to that lowest energy state. So over time, if you just set your qubits out on on your table, they'll all return to their ground state eventually. And so this amplitude dampening is sort of a way of representing that. So the first Krauss operator is actually the exact same as the phase. We have 1, 0, 0, square root of 1 minus gamma. But then the second is slightly different, and you'll notice that it has 0, square root of gamma, 0, 0. So that's our amplitude and phase dampening channels. Now we'll take a look at the third and final channel, which is the depolarizing one. And so depolarizing noise is basically a way of representing the operation that transforms our density matrix from itself to a combination of itself and the maximally mixed state. So this maximally mixed state is basically what you could consider maximal noise, where every possible state is mixed. So we have this represented here. I'll write depolarizing, dipole here. We have this represented here with 4 Krauss operators, and you'll notice some familiar terms. First, we have our K1, which is equal to the square root of 1 minus 3 gamma over 4, and this is times I, where I is simply the identity matrix. We will have K2, which is gamma over 4 times X, where X is, of course, the Pauli X matrix here. And then we have K3, which is, once again, gamma over 4 Y, and then we have K4, which is, once again, gamma over 4 Z, Pauli Z. And so you can see that then when gamma is 0, this results in all of these being 0, and so we're just going to have the identity matrix, which is going to result in no change. So it's going to map the density matrix onto itself. When we have gamma equals 1, you're going to see that these become the maximum mix. So you'll see that when gamma equals 1, this becomes the square root of 1 over 4. This becomes, right, the square, because 1 minus 1, 3/4 is 1/4, this is 1/4, this is 1/4, and this is 1/4. So if you want to get these results, you'll see that every single probability is equal. So it's maximally mixed. So in this case, we can see that this depolarizing channel with more Krauss operators has a lot more potential to induce substantial noise into this mixed state. Now that we have a description of both the noise modeling that we're going to be using and the metrics that we're looking at, let's actually jump into some Qiskit code. Okay, now let's jump into some Qiskit code. First, we have a lot of our standard imports. We have NumPy and a lot of Qiskit utilities, such as our quantum instance, our circuit, our parameters. But you'll notice some useful features that Qiskit has, such as a state fidelity function, which automatically computes the fidelity for us, in addition to all of the built-in noise functions that I mentioned with the Krauss operators. You'll see depolarizing, amplitude dampening, and phase dampening. In this work, we're also going to be relying on the BFGS optimizer, which is what's used in the paper. So now let's jump into some helper functions. We have our fidelity operation, which simply returns the fidelity between these two density matrices. And then we have our concurrence operation. So we get our density matrix, the original one, we compute this spin adjusted one where we have our Kronecker product of the Pauli Y matrices calculated up here, multiplied by the conjugate transpose, multiplied by the Pauli Y, and then we do these square root operations. You'll notice this try-catch block simply because matrix square roots can sometimes throw errors, so that's just in case they do. We then get the eigenvalues of this matrix, sort them, and subtract the largest here from the decreasing eigenvalues. So this is the exact definition of concurrence that we presented. We then also make a helper function to get this density matrix where we have our parametrized circuit, we assign the parameters, the specific numbers, and we bind them to our circuit. We then save this density matrix, run our noise model, and then get the actual values for this density matrix. So this is just a helper we're going to be using, which is important when you have noise and parameters. So first, we're going to be looking at the figure 2 in the paper and how we can sort of approximate that in Qiskit. The first thing we're going to want to do is make the circuits that are described in figure 1. So there's 3 different versions. They all have the RY gate and then the controlled NOT, but then differing numbers and qubits for the second set of RY gates. So we have these different version controls here. You can see it's just a small 2-qubit quantum circuit that has a varying number of parameters. The second version has RYs on both qubits, whereas the first 2 versions only have RYs on 1 qubit. So there's different numbers of parameters. And then we can create our Hamiltonian, and this is using the OptFlow part of Qiskit, where we say it's simply a ZZ plus XI plus IX, all with no constants in front of them. We then specify our noises that we care about, which we already imported, the phase, amplitude, and depolarizing noise. We then specify what noise levels we're looking at between 0 and 1. So we take 100 points between 0 and 1 to look at those different noise levels. And we're just going to be using a simulator here to evaluate these results. One thing to note before we get in any further is that in the original paper, they do a lot of work in the absence of shot noise, so you get the exact analytic expectation values. We're working here with stuff in the presence of shot noise. You'll notice that up here we have a tool to get the density matrix. If you wanted to work in the absence of shot noise, you could also get the state vector and calculate all the analytic expectations are from that state vector, and you could get that result as well. However, we proceed here just using the shot noise present because not only is it simple to implement, it's also more realistic, right? All quantum hardware, even noise-free quantum hardware, has shot noise. So now we go through all of these noises that we care about. We go through the different circuit versions, and we keep track of the metrics that we care about, the energy, the fidelity, and the concurrence. So the first thing we're going to want to do is just provide a method for evaluating the expectation and the gradient. And this is, once again, using these OptFlow techniques where we combine the parameters with the values that are assigned to them, and then we sample from it and get the result. We do a very similar thing for the gradient, just with this defined gradient function. So we can make the circuit for each version, create our noise model, and then get the results. Inside this noise model, it's very simple to create in Qiskit. You simply instantiate it and then add whatever type of noise you would like. In this case, the noise is following the C0 gate. So we want to specify here if this count refers to which noise model it's operating with. So this is the depolarizing noise. We want to specify that this is on the 2 qubits. That's what this number refers to. Otherwise, we're using single qubit noise in the amplitude or phase dampening, and so we're going to want to do a tensor product of those noise so that we can actually apply it to 2 qubits. So then we're going to specify that this applies to the qubits after the controlled NOT gate. We can then make our quantum instance using this noise model, create our circuit sampler, and get our expectation value by combining the Hamiltonian we previously defined with OptFlow and taking the product with the state function of our circuit. We then specify our gradient technique, which is just going to be our standard parameter shift rules, and then we're going to convert the operation that is this Hamiltonian and convert it for this gradient-friendly technique. We're then going to specify that we're using the BFGS optimizer, and then we're just going to call the optimize function, saying that these are our number of parameters here. This is the function that we're actually trying to minimize, right? We're just trying to minimize the energy of this Hamiltonian. This is how we're evaluating the gradient, and we have some initial parameters. They're simply randomly generated. We then append whatever the final result is to our energies that we're keeping track of, and then we look at the fidelity. So the fidelity, we have to compare it to something, right? The fidelity is a metric that compares 2 states. So we look in the noiseless case, which would be the ideal, whatever we can get to optimally would be without any noise. So we say that we're comparing our current density matrix to this noiseless case, which would be the optimal results that we can achieve. So we get this fidelity between these two density matrices using our helper function. We then get the concurrence of our current density matrix, once again using this helper function previously defined. Then we have a lot of plotting functionalities that just is helpful to make all this look good. And we can see here the results that are generated. You'll notice some striking similarities between this and figure 2, even though there are some differences. For example, you'll notice this seems to be a lot more noisy and variable than that, and that's, as I mentioned, likely due to the introduction of this shot noise. But you can see that the trends all remain the same. In this case, 0 and 1 refer to the two circuits which have only one RY gate following the CNOT, and 2 refers to the circuit with the two RY gates following the CNOT. So we can see that in the presence of amplitude and phase dampening noise, even in the presence of very high levels of noise, this is the highest level of noise you could have in this case, we can see that the energy remains surprisingly low or relatively low. However, we can see that in the presence of this much noise, the concurrence in both of these cases for all circuits decreases. So this tells us that even though the energy is remaining very low, which is what we want, the concurrence or the entanglement is decreasing. So this means that if we want to scale this up, the entanglement clearly isn't that important for achieving the minimum energy state. But if the entanglement would be important, then our energy would likely reflect that. So this is helpful for informing us when we want to scale these methods up. We can also see the fidelity of this circuit that has multiple RY gates remains relatively close to 1, no matter how much noise you have for the amplitude and phase dampening. Of course, in the depolarizing noise, we can see that this is consistent for all the circuits, that more depolarizing noise results in less energy, more energy, less fidelity, and less concurrence. So what this tells us is that when you're converting it to this maximally mixed state over here, which is what happens at 1 in the depolarizing noise regime, that it doesn't matter what your circuit looks like because it's already, no matter what, going to be this maximally mixed state. So we can see these results follow similar trends to the presented figure 2, but there are some little differences. Next, we're going to be looking at the 4-qubit system, which has a circuit described in figure 3 and results described in figure 4. So this time we're only caring about one circuit, which has 4 qubits, RY gates followed by 3 CNOTs followed by more RY gates, and each of the CNOTs is followed by noise. So we can represent this very easily. We have 8 parameters. We do the first set of RY gates, then our CNOTs, and then our second set of RY gates. And then we once again have a Hamiltonian that we're going to create using these op flows. If you notice that the ordering looks slightly different for the IZ-IZ, and you might think it should be ZI-ZI, remember that this is Kiskit ordering, so we have to order it in this way. And then we see that we have our X, Y, X, Y components of this Hamiltonian. So this is a more complex circuit and a more complex Hamiltonian that we're now going to be looking at. So we can see, once again, we're considering these phase, amplitude, and depolarizing noise channels. And then we're also going to be looking from 0 to 1, once again using a simulator. This code is once again very similar to the above, where you have the same exact evaluate expectation and gradient functions. We have the exact same optimizer function, expectation function. All of this is the same. The only slight difference is that we don't have the concurrence here. And that's because the way I described it was only for these 2-qubit systems, but now we have 4 qubits, so we're not applying it in this context. But everything else remains the same, and you can see that in this case we even have the same application of noise following the CNOT gates. Note that we don't need to actually specify 4 qubits here because we can add them to all qubits using this add all qubit quantum error function. So this remains extremely similar to the above code in all of those ways. And once again, we have some plotting functionality. And here, once again, we can see some similarities to the figure 4 results. We can see that as this noise parameter increases, the energy once again goes to 0 in the case of depolarizing noise, and goes to around -1 in phase and amplitude dampening scenarios, or around -1.5. We can also see that in all noise scenarios, as it increases, it goes to very low fidelity, decreasing rapidly from 0.2 to 0.4. And so you can see that this aligns, even if somewhat more noisy, with the results presented in the paper. Once again, this tells us that even though the energy doesn't reflect as starkly as the fidelity does, the scaling of this may be important. Specifically, even if we're able to get okay energy results, even if we're okay with an error of around -0.7 or so from our ideal energy, our fidelity with this optimal state is extremely low. So if we were to increase this system size where fidelity is now an important metric and a relevant metric, so we need high fidelity to be able to get to this low energy state, we're not going to be able to actually get there because fidelity decreases so rapidly. And that's something that isn't reflected in the energy. So if we just saw the energy, we might think, oh yeah, we can scale this up. Whereas if we see the fidelity and we realize that this fidelity is probably going to be important for some energies, ground state energies, then we will not be able to scale this up in the presence of large noise. And so that's the importance presented of these metrics, of these different metrics. Now we're going to be looking at so-called parameter degeneracies. So this is going to be zooming in on figure 5 right now. And this is really shown as redundant parameters. So we have this 1 qubit circuit where we have 2 RY gates, and by default this contains parameter degeneracy because clearly you can achieve the same operations with 1 RY gate as you can by 2 following each other. However, we're going to be looking at the case where there's some noise in between these RY gates, specifically phase dampening noise. So the first thing we want to do is actually create this circuit. It's a very simple 1 qubit operation with 2 parameters. We specify the label for this first RY gate because this is going to be the one that the noise follows. And then we say that our Hamiltonian is actually just a Z operator, right? We're just measuring this 1 qubit. We specify the noise level here to be a pretty high 0.4 noise for this phase damping. And then we have our simulator backend. We're going to specify the expectation evaluation function, even though we're not going to be optimizing this at all. We're just going to be plotting how this parameter dependencies look. So we first create our noisy model, or our noisy circuit. We instantiate our noise model, we add our phase dampening error, and then we add this to our first RY gate. Once again, this is very similar ideas. We specify our quantum instance in our circuit sampler, we convert our operations, and then we can get our results. So we iterate through, in this case, 30 versions of this parameters. And so we look at the x and the y's, and where x is actually the first RY and y is the second RY. And then we evaluate this expectation value at each of these possible parameters. Then we repeat this process in a noiseless scenario. So once again, we create the quantum instance, but this time we have no noise, and we repeat this evaluation process. We can then plot them, and we see evidence of the parameter degeneracies here in the noiseless case based off of this symmetry. You can see this is very much a symmetric plot, but we can see that the phase dampening error actually breaks the parameter degeneracy. So you can see that this is a non-continuous sort of thing, and there are definite minima that exist that didn't exist before, right? This was all one continuous valley that is in this function space, but now this has been broken by the phase dampening error. So this indicates that this is potentially an important consideration for different types of error, is this redundant parameters, over-parametrization, or this degenerate parameters. It's worth noting, however, that if you repeat this, and you can see above how to do this, simply change out the noise type, with the polarizing or amplitude dampening, that these two types of noise don't actually break the continuous parameter degeneracy. So that is something else to consider. The last consideration that we want to make is for random target states. And in this case, we're only going to be looking at the optimization of a single random target state rather than like 1,000, which is presented in the paper. And so in this case, we have, as detailed in figure 6, a 4-qubit system of an arbitrary number of layers with RY gates followed by controlled NOT gates with noise after the first two and the third. So we specify, in this case, we can't put noise after every single CNOT. We want noise after specific ones. So we specify by labeling these CNOTs that we're going to have noise after. Then we consider, once again, the same 3 sets of noises, but with a reduced set of the noise levels to very realistic numbers. And then we also vary the number of layers, so how many times we repeat these blocks of RY gates and noise gates. And then we, once again, are going to be simulating this. We create a random target state and get its density matrix. Note that this is, once again, a single target state. And then we're going to be looking at the cost function that's the difference between 1 and the fidelity, right? Because a fidelity 1 would be perfect matching of the state. So if we want to minimize that, we don't want to minimize the fidelity, we want to minimize 1 minus the fidelity. So the minimum is at 0. So we want to maximize fidelity, in other words. So in this situation, we now can see very similar noise modeling that we have here, which is, in the case of depolarizing noise, we specify it on 2 qubits. In the case of amplitude or phase dampening, we once again do the tensor product, and then we specify which CNOT gates it's operating on, which are the first and second labeled. We then want to look at the first 2 rows of this figure 7, which are the reoptimized fidelity and the non-reoptimized fidelity. So what this means is that we're optimizing it in the absence of noise. So you'll see this evaluation expectation noiseless, where we're getting the fidelity optimization routine without any noise. And so the non-reoptimized then just simply applies this and looks at the density, the noisy evaluation. So if we have our optimized result here, we get our final density matrix with the presence of noise when we didn't optimize it with noise. So then we make that comparison and get the fidelity to our target state with noise for the first time. In the reoptimized version, we do a very similar thing, except we actually look at this noisy evaluation first. So we optimize it the exact same in the noiseless case, but then we say, okay, now let's add noise and re-optimize it, hence the name, with noise, and then we'll evaluate it also with noise. So this evaluation is the same, and the first step of the optimization is the same, but we have a difference here in the fact that we also optimize it with noise. And we can see the results here, once again with some plotting features that show what is effectively that the non-reoptimized fidelity is a lower bound, in the sense that in the presence of noise, you're not doing any more optimization. So that's sort of the worst case scenario, whereas reoptimized adds the optimization, so it's sort of an upper bound. And in this scenario, we can see an interesting result that depending on the presence of noise and the level of this noise, adding more layers is not always a good thing. So we saw earlier that parameter degeneracies might be useful for working with noise, but now we can see too much of a good thing is not always good. And we can see that at very low levels, of course, increasing the number of layers increases the ability and the ease through which we can access our target state. But increasing the number of layers in the presence of noise also increases the amount of noise. So the more and more noise we have, the more and more we're not able to achieve our desired results. So you can see that in the higher noise cases, represented here in green, red, and purple, that this is going to be decreasing as you increase the number of layers. You can see this here. Green only slightly starts to decrease with the 0.01 noise, but both the 0.05 and the 0.1 noise decrease pretty rapidly, especially in the presence of depolarizing noise. So that's been all of the major ideas we have here implemented in Qiskit. We discussed how to do this both theoretically, and we have now presented the code. So that's been our review of the paper evaluating the noise resilience of variational quantum algorithms. You can find all the code and the paper down in the description. I've been your host, Owen Lockwood. Thanks so much for watching. See you next time.